inversion, what you talk about. So today I'm going to talk about the rock physics side of things, which is my specialty. So just I don't know whether you need to mention our group. Right now we have about 12 people, I think. You know, about 6 postdocs, visiting scientists, and 6 graduate students, and maybe more. I don't know. I think and so just two faculty, Elita, myself, and as you all know, Elita was much more involved in the seismic wave propagation and imaging aspects of things, and I'm much more of a rock physics person. So we complement ourselves to us very well and work very well together. So today I'm going to talk about another aspect of the work in our group, and specifically this is done by our graduate student Nan Yu. Okay, or Yunan, we call it, that's his Chinese, just her Chinese name, and Shale and anisotropy model building based on deep neural networks. Actually, I'm going to talk about 2 aspects of things. One is the Shale and anisotropy estimation based on a crack model, which called the Cheng model, and then the 2 different methods, the inversion method and then a regression using neural net. So the inversion method is a JGR paper published last August, and I'll give you a reference date at the end. And the neural net method is just got published at JGR this month. Okay, so both are JGR methods and in JGR papers, and those are part of collection in the Joe Walsh Memorial volume. Okay. So just a very quick background. Why do we care? Why do you want to estimate shale and anisotropy? So anisotropy is really essential for seismic processing with wide azimuth, long offsets, and multi-components, and it affects things very simply. You know, just about everything we do in terms of trying to image things, right? From microseismics, locating where the events are, to estimating actually the rock properties of the shales. You know, the anisotropy plays a big part of it. You know, shales are the most common and most anisotropic rocks, and they're used to really, up to about 15-20 years ago, only considered as cap rocks and not as source rocks. And of course, the revolution in shale as a reservoir started right around 2000, okay, with Mitchell energy, and they start cracking, fracking the shales to directly draw out both oil and gas, mostly gas, but still quite a bit of light oil from there. Okay, so now shales are both reservoirs and cap rocks. So properties of shales needs to be studied quite carefully. Now, typically we look at this, any kind of rocks, we look at it 3 different ways, right? At the core scale, right, we drill a hole, get the rocks out, and actually go in the lab and measure them, the properties. Okay, yeah, the latest using digital rock, we can now look at really micron or sub-micron level, very detailed what these rocks are. The second part of it is once you drill the hole, we can go there and put in a tool to measure different things, like, well, you can't see it and I can't see what they are, but typically you have porosity, density, and velocities, a vertical velocity, PV and VS. These are vertical rocks, and typically Most of the exploration wells, you would not have a deviated well. You basically have a vertical well, and you just go in and measure standardly velocity, the vertical velocities and density and porosity. Okay. On the seismic data, especially a y offset, then you can measure propagation as a function of angle. So you have three different things. So the question is, how do you make sense of all this? How do you put together all that? And seismic, of course, is wide coverage but low resolution. So for cores, okay, it has high reliability and resolution, but you never get enough cores, okay? And it's not in situ. It creates quite a bit of a problem because in shales especially, it's very difficult to recover cores in the condition is in the earth. When you getting out of the earth because you're unloading the stresses around it, sometimes shales tend to delaminate. And if you don't actually preserve the cores properly, the shales tends to dry out, right? They change the mineralogy, okay? And shales tend to be brittle, like this example here. It actually, let me see, yeah. It actually, you can see some naturally it delaminates and breaks into different pieces. So, and up to recent experiments, most of the shale and anisotropy measurements are done on 3 different cores. Okay, a vertical core, or a horizontal core, and a 45-degree drill core. Well, you can see from this picture, it is not that homogeneous, the rocks. And so it's hard to really compare the 3 samples properly. So those are the challenges from the core side. From the log, basically, we measure for vertical velocity. You really don't have any measurement, easy measurement on the horizontal velocity. Okay, as a matter of fact, it is on the vertical well, it is impossible to measure the P wave anisotropy. Shear wave anisotropy we can if we have a stony wave measurement. Okay, we can do that. The new tools can do that. However, most of the logs being run out there, even the modern logs, a lot of times they would not have a stony log, or you're stuck. Okay, so you basically VP and VS logs. Typically, that's what you end up looking at. Okay, so there's no direct measurement. It's high resolution, but it's not as high as the core. Okay, and it's sparse, right? Just the cores, because you don't drill that many wells, especially in the exploration sense. Okay. So, and then when we get to seismic data, yeah, you have really wide coverage, but it's low resolution. Okay, you're looking at 10 to 30 meters resolution. Okay, so you really, if you ever look at a core and imagine a 10-meter resolution of that, you can see how much variation there is, and you're actually averaging a lot of these properties. So when we take the well log, and what we want to do and use well log information as a prior information, and have us constrain the seismic data. Okay, so now how can we do that? One of the things that we hope to be able to constrain is can we for example estimate the P wave anisotropy for here. What about the NMO term? Okay, can we do that? So this is what is that all about. So we are trying to do velocity and anisotropy estimate based on a model, because without a rock physics model, you cannot measure the anisotropy. Okay, so the question is, can the model help you get an estimate of the anisotropy? This is very common in well logging. You assume a model and try to get some information on there. So the first one I will talk about the inversion method. This is the last year's JGR paper in August. So basically, how do we form a model? So we imagine an intact rock like this. It will be composed of an isotropic rock matrix, okay, plus spherical pores, or what we call stiff pores. These are the porosity that is basically very resistant to deformation. All right, and then we have also the align cracks. Align cracks are imagined to be things that are skinny and much more response to deformation, at least in the vertical direction. Okay, so we have an isotropic background which is composed of the isotropic rock matrix plus the spherical pores, and you combine that as isotropic background. Okay, so background bucket shear moduli. If you look at the written in terms of the stiffness matrix, these are the C0 Cij0s, and then the align cracks, we put it as a first order correction C1ij. Okay, why do we do that? Because we think that the cracks are not really dominating system, is a first order correction to the background system, isotropic system. Okay, so the intact rock, the effective moduli is equals to the background modulus plus the correction. Okay, actually there are higher order terms, and in Hudson's paper and also my paper in 1993, you see the corrections, high order term corrections. Hudson just did a Taylor expansion, which turned out not to be stable, and I corrected it and using a per day approximation, which is a much more stable correction term to that. So we also express this in terms of a crack density, which is for a penny type shaped crack or prolate spheroid. This is the crack density is equals to 3 times the crack porosity divided by 4 pi alpha, which is the aspect ratio. The aspect ratio is the height of these ellipsoids divided by the width of these ellipsoids. And these are usually of the order of a tenth or 100th or something, you know, that kind of a 0.1, 0.01, etc. Okay. Okay. So, what is the advantage of using such a crack model? And the advantage is, you will see as we develop this, is that using this crack model, we can show that there is sensitivity in the vertical measurements. So we can go ahead and model that. So the effective moduli from the well log and the vertical measurements, okay, is basically C33 and C44 in terms of the stiffness matrix notation. Okay. The background moduli, what we do is the K0 and mu0, which are the matrix moduli. These are moduli from the minerals itself. Okay, and then fluid moduli, which is the inclusion. Okay, and then the porosity. And this is a very straightforward combination of the matrix property plus the stiff pore. Okay, the phi is the porosity of the stiff pore. So, and we can calculate it very easily using a very standard technique called the Harshin-Strickman upper bound. Okay, so K is the bulk modulus, mu is the shear modulus, the Harshin-Strickman upper bound. We take the matrix moduli and the fluid moduli and calculate what the background isotropic moduli should be. Okay? And in terms of Lamé parameters, the isotropic component of C33 is lambda plus 2 mu, and the isotropic components of C44 is just mu, right? Mu, this is the lambda mu, the Lamé components. So then you go to a second part, which is the first order corrections. So it's C11, C44, C33, C44, C11, and C66, and there's also a C13 term that we can calculate. Okay, but the key is you're looking at the C1, C33, and C44 term, the correction to the isotropic background of the vertical measurement. The correction, the C33 and C44 term, they are both linear in crack density. Okay, that tells you that there is sensitivity of the vertical measurements to the crack density. As a matter of fact, the horizontal measurement of shear, C66, correction is just 0. Okay, so the shear anisotropy is purely defined by this term, C114, purely. Okay, and you look at the P wave anisotropy, which is the contrast between C11 and C33. Looking at the correction terms, okay, if you think of a Poisson solid, which is lambda equal to mu, this is what? This is 3 squared is 9, right? Lambda equal to mu. This is 9 times the crack density times this term, U3. C11 correction is just lambda square, one time square is 1 times the crack density. So this correction term turns out to be 9 times this correction term. So you can see the sensitivity of the vertical measurement to the crack density is there. That is what allows you to actually estimate the anisotropy from a vertical measurement, right? If it's the horizontal measurement, then the sensitivity is gone, mostly gone, and you cannot really do what we do here. So now understanding the model is sensitive to C33 and C44. So we have these unknown parameters, which is K0, mu0, the background modulus, aspect ratio, and crack density. So we define the objective function. This is the inversion part we talk about as this. So what is this? This is the crack density estimated from P wave or C11 and C33 or C33, and this is the crack density estimated from the shear measurement. We want the difference between them to be minimal, so they're consistent with each other. So this is the inversion setup. Okay. And then we try to estimate, once we got that, these standard anisotropy parameters, which is epsilon gamma, which is the P and S wave anisotropy, and delta, which is the NMO correction. Okay, so you can see delta is more complicated combination of different terms. Okay, and their sensitivity of this is actually instead of just simple direct measurements, a combination of subtraction and addition, and you can see this is more prone to error, and you see it actually in the data. So the first thing we do is, if we do, this is a set of lab data from Wernick and Lewis. We collected a subset which we believe is roughly the same depth and the same rock. And do the inversion, we obtain the inverted parameters K0, mu0, and alpha. So this is a straightforward Monte Carlo grid search type of inversion. Okay, nothing really fancy inversion. But you can see the model C33 and C44 and the measure C33 and C44 are fairly consistent with each other. The estimated epsilon, gamma, and delta from the model and the measured epsilon, gamma, and delta, for epsilon and gamma, they're fairly consistent. Delta is all over the place. As I mentioned, delta is really very susceptible to noise, okay, and error in measurement. And also because, as I mentioned, for the core, back in those days, the cores are from 3 different actual cores, okay. So the 45-degree measurement from which they obtain the gamma delta is also get most of the error in it. So this is actually fairly true for delta is notoriously a difficult to obtain measurement in anisotropy rocks. So this is applying the field data. This is a well in the Sichuan Basin. So we have caliper, Vs, Vp, rho, density, porosity, and this is the gamma ray. But most important for us is we have a mineralogy rock to give you some idea of what these things are. So for example, this section got more clay in it, and this is this section. This is more quartzite down here, and here there are certain intrusion and quartz up there, and in here somewhere there's some dolomite floating around. Okay, so what we did was, for the inversion, we divided it into 5 different depths. Okay, we have to assume the K0 and mu0 and alpha are the same. This is a huge assumption. You can see within each layer. That's a big assumption, but we can't really get away from it when we look at the inversion algorithm. All right, and well, you can divide it much thinner, but yeah, that takes a lot longer time to do the inversion. So we did that. We did just divide it into 3 different layers, 5 different layers. And in here, this is a probability density plot for a range of K0, mu0, alpha, and then we're putting this, pick this as mu0, K0, and putting alpha. This 3 points that we picked, if you plot it over in the K0 versus mu0 space, it's sitting here. It is at a minimum, but you can see the minimum is actually quite wide. Okay, you can probably very easily move around it a bit more without really affecting a lot of things. This is the same alpha in there. Okay. So, but we go ahead and pick this and see what it looked like. So for the 5 different layers, okay, we have 5 different inverted K0 mu0 combinations, as well as 5 different aspect ratio, ranging basically all around 0.02. Right? It doesn't really vary that much, you know. So, but interestingly, between C44 and C4, and C33 and C44, from the inversion and from the measure one, because measure is what we actually do in the log, right? That's from the VP and VS. They agree quite well, except when you get to really high velocities. Okay, at the higher end of the K0 mu0, we are not getting the high end of C33, I should say. We're getting some bend over, telling you the inversion is not fitting quite as well. And this is the anisotropy log. Okay, this is epsilon, gamma, and delta. As you can see, delta is really small, a lot of sensitivity to what is in the formation, but alpha and gamma look reasonable. There's some anisotropy in epsilon and gamma and gamma. Okay, so we don't actually have a ground truth to it, and so this is the result we get. So that seems consistent and fits the vertical measure velocity quite well. So this is the conclusion of our first paper. The inversion algorithm is a feasible way to estimate the anisotropy. So, but we're not quite happy. We need to, the main thing is the division into different layers is arbitrary. And where we actually pick the K0 and mu0, because we're picking it on a very flat objective function, is a bit also arbitrary. Okay, so like everybody else, we say, okay, my machine learning can help us address some of this problem. So we start looking at it using neural net. Okay. The way we approach it is actually fairly different, because in a lot of the geophysical measurements and in well logs, in this particular case, we just don't have a lot of data. Okay, we don't have a lot of, I believe what is called the features for us to do the learning on, to get the associated label associated with it. So in this particular case, what we're going to do is taking rho, density, porosity, VPVS. We actually double down using C33 and C44 in addition, and then coming out as a K0 and mu0 and alpha. So C33 is rho VP square, C44 is rho VP VS square. So these are basically additional weight combinations on the velocity we're coming in. So the feature normalization is we taking these kind of features, okay, and basically normalize it. And once you get out, which is another normalized set of K0, mu0, and alpha, and then we denormalize it again, okay? And then you get, and then from there you can calculate epsilon, gamma, and delta. Now, because we don't have actual measure ground truth, what this paper and what our approach is different is we use the Hudson-Cheng model to build the learning set. Okay, so the learning set is completely synthetic. Okay, completely artificial, nothing to do with actual measure logs. Okay, so we use the model to generate a whole bunch of these things, and then the well logs are basically correspond to V0, Vs, rho, and we don't actually have the logs in the training set. So this is the sampling range for rho, the density of the matrix. Okay, the porosity, aspect ratio, K0, mu0, and crack density. The actual density in a rock is the arithmetic average for the matrix density, rho m, and the fluid density, rho f, okay, for a given porosity. So we use these parameters, and these are the lower bound and upper bound, porosity, okay, K0 this range, and mu0 this range, and aspect ratio this range, and crack density over this range. Okay, so we did that, and we have 27 million samples to generate. That's something that we will never have in log data. Okay, you're lucky to get 10,000 per well, right? And how many wells you need to get 27 million? A lot of wells, right? And it doesn't cover the whole range of the data what we're doing. Okay, we use this sample, take 70% of them as a training set, and then 20% as a validation set and 10% as a test set. Okay, so in the training set, we take at epoch 21, which give us the smallest validation value, validation loss. Okay, can use that to test our data. Okay, so this is how we're doing it. Okay, so give you some idea, training data versus actual. So this is C33 and C44. This is the distribution of our training data. Okay, how dense the C33 and C44 sample in the training data set, versus the red one is from the Chinese well log, and the yellow one are from the US well. So the Chinese well that we're going to play around with, and the US well, they sit quite well within the sampling range of our training data set. Whereas the rock lab data kind of a little bit more biased. Okay, and this is not so bad, but this is worse on the epsilon and gamma plot. Epsilon and gamma plot, we're still staying fairly well within the range from the well logs, okay, compared with the training data set, and but the rock physics model, rock physics measurement, the lab measurements are out of range, out of bound. Okay, so what we actually did for the rock physics, the lab measurements, is when we do the normalization and denormalization algorithm, we use the distribution of the rock measurements itself instead of using the distribution from the synthetic data. Okay, so we normalize within the mean and variance of the measured data itself rather than on the synthetic data. Okay, so this is what happened after we do that. C33, C44, this is a DNN prediction versus lab measurements. They actually fit very well. And epsilon, gamma also fit very well. What is not fitting as we expected is the delta. Okay, delta still remains a challenge. All right. So how does that perform in real data? So we look at this and we have done the inversion, right? Remember, we have done the inversion on this data set. All right. So this is a Chinese well data set. So we're going to compare. So this is the inverted C33 and C44 against measured C33 and C44. And this is the DNN predicted C33 and C44 versus the measured. Okay. The C3, the DNN predicted ones are much tighter. Okay. And I'll show you why a little bit later. Okay. So, the next page actually. So what happens is when you define an inversion, remember we broke it into 5 different layers with constant alpha, K0 and mu0. So this is a plot of the inversion result, which is blue, and the DNN results, which is red. So in the inversion results, we look at K0 and mu0 because we block this thing in 5 different blocks. So within each layer of the 5 layer, they're constant. Okay, this is K0 and mu0, and that alpha also constant. So all the variation you're seeing actually ended up being assigned to the crack density. You understand what I'm saying? Okay. The variation, the typical variation with depth are no longer assigned to each depth, but assigned to just the crack density, looking at the blue line, right? Now, you look at the epsilon and gamma, they're actually fairly consistent for the 2 methods, for the inversion and the DNN. It's just what they assign it due to. Now, in the DNN predictions, okay, you can see, because it's a depth-wise inversion, you apply the network to actually each depth, you just apply the network going through, you can see that the variations are there. So the DNN, the network actually captured the variation in the data in K0 and mu0 and alpha.
You mean it also fits the noise? The DNN also capture the noise?
This is not noise. This is actual data. So this is not noise, okay. Right? I mean, because I have this to guide me. Oh, so right? This is the mineralogy, yeah. Right? So these variations are not noise. These are actual changes in the mineralogy.
Yeah. So the inversion results more smooth.
The inversion because you're assuming this is a block. Right, so you're averaging the mineralogy all like this, right? Yeah. So basically you're assigning everything, this variation you see to the crack density in the inversion, okay? Whereas the network is distributed in addition to crack density, also to K0 and mu0, okay, and alpha. Okay, but the resulting anisotropy measurements are actually very similar. Now, why do I like this better? Why do I believe the network better? I will just show you the next plot, which is this. I flip this to give you a better visual comparison. Okay, here I'm plotting it like this because I want to associate clay with the anisotropy. You can see the clay and the anisotropy has a bit more relationship. You see that? But now, when I do this, I want you to focus on the quartz. And you can see the quartz content, the volume, agrees very much with K0. Okay? So I have no idea what K0 is. It's not an input, nothing. But from the log measurement, I was able to extract, the network was able to extract the variation in K0 that actually agrees fairly well with what you see in the quartz. Because quartz is the hardest component of, harder of the two main components. You don't really look at the dolomite, right? So more quartz is higher K0. And basically that's what you're seeing in the network results, okay? The network does not know anything about this at all, but just that from the measurements, they were able to tease out this component, which to me is a very gratifying result that's saying the network is actually seeing something that is there, that we cannot get it easily. So that's the advantage of having a neural net. So this is a beautiful example, and this is really, don't forget, we didn't train the network based on the data. We train the network and then apply to the data. So that's the beauty of it, right? This is the US well, and once again we divide it into different sections. And this is a comparison with the inversion versus the network. And once again, for the C33 and C44, the network is doing better. Now, in this particular case, the agreement in epsilon and delta is more qualitative than quantitative. Okay, the shape is there, actual numbers are varied. Okay, so, and this one I don't have a mineralogy log, so I don't know whether these are realistic, but I have more faith in this one. After seeing the last example, I have more faith in saying K0 mu0 represents some variation in the mineralogy, right? This is aspect ratio, this epsilon, gamma, delta, okay? And this is crack density. Okay, so it is a very interesting result. So we have one really nice result. This one is may not be as nice when compared to inversion, but there's nothing for me to believe one approach over the other, except that from the previous data set, I tend to believe the network more than just the direct inversion. So let me just do some conclusions, and then we can talk, answer some of the questions. So we use the lab data to validate our approach, and then we use the well log data in US and China in two different ways, from the inversion and the neural network, and then we see that they give you roughly similar results. Right, based on our model, inversion and neural net approach are proposed for Shale anisotropy estimate for vertical wells. These two methods produce consistent results when applied to lab data and field data. Right, the estimate and anisotropy agree reasonably well, and with the lab data, and reasonable and so consistency with well logs, with the mineralogy logs. So some of the things that we're thinking about, what are the pros and cons of different method. So this is a model-based method, right? The inversion is, you know what you're inverting for, what is your model. Inversion is fairly quick, but you have to assume K0 and mu0 and alpha for the same layer, and repetitive. Well log sublayers, tuning, search for parameters, and this is fairly subjective. Okay, and selected inverted K0 as subjective for each layer, right? For the neural net, it's a pure data driven method. It's hard to interpret, although this is also model based, because we train the network based on the Hudson-Cheng model, right? It's a bit time consuming in training the network, right? The pros are good generalizability, predicts reasonable anisotropy model for 2 wells in 2 different basins with 2 different continents, with no modification and no training on these wells, right? And good efficiency. So this is very important. Basically, assume you're thinking about putting something like this on your truck. As the data comes up, you're not only getting VP and VS normally, you can immediately run the network and get the anisotropy parameters right there in the field for delivery. So that's, to me, is a very, very valuable thing. Okay, yes, it might not be truly, the actual number might not be true, but I give you a good estimate on where you're seeing anisotropy, right? So these are the 2 references. This is Li, Cheng, and Yu in 2019 from GGR Solid Earth. And then now this is Yunnan. Well, this project we started between Lita and I before Yunnan joined us as a graduate student, and then she's been working on deep neural net applied to this, and this is the paper that just come out. Okay, thank you, and welcome to have any questions. Yes.
I have a question on how you generated the synthetic data to make sure it looked like real data.
We did not get the range to make sure it looks like real data. We just asked ourselves, what is the range typically we see in these minerals, in what the porosity range likely to be, that kind of thing. So we can see we had a fairly large range. We end up 27 million data points. We can even expand it more and cover even larger area, you know. So.
And so for that, you specified the formation, the different layers that are there.
The new one, we don't specify anything, except, you know, the if you recall, the model inputs are basically, these are just the model input, right? And we just put this, right? And then you estimate your outputs are actually K0, mu0, and alpha. You know, so you actually just input the whole range of using the model, right? Basically, give you matrix models, porosity, aspect ratio, and you can calculate what the velocities are. That's how we generate it, basically. Yeah. Yeah. Yes.
I have 2 questions.
Yeah.
The first one is, do you think it's fair to compare the inversion-based method and the machine learning method in terms of data fitting?
Yeah, I think we are. We're comfortable with that because they're basically the same model.
Because you
It
only
is the
use
same
5
model.
layers for the inversion. So if you use 100, 200, maybe.
Yeah, but then it will take forever for you to run the 100, 200, right? That's the whole point. We want to agree. I mean, conceptually, if you just define it really thinly, you could generate back kind of what neural work is generated, but then it will take a lot more time So what we think, the whole project is, can the neural net speed up that process and allow you to use the same conceptually, the same model to model the data instead of going to be a tedious work of going through inversion every layer, then you're doing this, right?
So the advantage is its efficiency, not in terms of data feed.
Yeah. I mean, really, is advantage is efficiency. I don't think it's really data fitting, although it does. When you do the inversion, you have to kind of, because of the minimum of K0 and mu0 is kind of fairly broad, and you a lot of times you have to make some subjective judgments of where you pick this. Whereas a neural net, because it's been trained on a much larger data set, you kind of trust the way the net is actually picking the K0 and mu0, and when you apply the data and compare it with the meteorology doc, it gives you some confidence that actually these are the right approaches, that the net is actually picking the right thing. So.
Yeah, the second question is, how can you make sure that the neural network is just memorizing stuff?
It's good. You can look at it that way. It's just memorizing that when I have VPVS is like this, then the output should be like that. That's what learning means, right? That's what learning means in some ways, yeah. Other questions? Anybody online?
I haven't got any questions yet.
Well, as I said, you know where to find me. I do have a Yale email address. Just feel free to send me questions later. Yeah. Okay.
Thank you.
Thank you.